Since the 1980s, one diesel engine has powered everything from long-distance passenger trains to the heaviest freight locomotives in North America. It's pulled unit coal trains through the Rockies, hauled intermodal consists across the plains, and moved commuters through cities from coast to coast. It's worked in brutal desert heat and Arctic cold. It's proven itself in service that would break lesser engines. And 40 years after its introduction, it's still in production, still being installed in new locomotives, still proving that good engineering never goes out of style. This is the story of the EMD 710 engine. It wasn't the most revolutionary design EMD ever produced. It wasn't the most powerful engine in the world when it was introduced, but it became one of the most successful diesel engines ever built for railroad service, redefining what modern locomotive power could be. Compact, powerful, reliable, and adaptable, the 710 took everything EMD had learned over 5 decades of building diesel engines and refined it to near perfection. The 710 powered a generation of locomotives that transformed North American railroading. It enabled the AC traction revolution that changed heavy haul freight. It provided the power for modern passenger service that connected cities and suburbs. It proved adaptable enough to meet increasingly strict emissions standards while maintaining the reliability railroads demanded. And today, decades after the first 710-powered locomotive entered service, these engines continue working, continue being rebuilt, and continue proving that sometimes evolution beats revolution. This is how the EMD 710 engine redefined modern diesel power. To understand why the 710 was significant, you have to understand what came before it. The story begins in 1938, when Electromotive Corporation introduced the 567 engine, a designation that came from the displacement of each cylinder, 567 cubic inches. This was the engine that would make diesel locomotives practical for mainline railroad service. It was a 2-stroke design, meaning each cylinder fired once per revolution, rather than once every 2 revolutions like a 4-stroke engine. This gave it smooth power delivery and excellent low-speed torque characteristics, ideal for moving heavy trains from a standstill. The 567 engine powered the locomotives that killed steam. The FT freight units that proved diesel could handle heavy mainline service used 567 engines. The F units that became iconic symbols of American railroading were 567 powered. The first generation of road switchers, the GP7, GP9, SD7, SD9, all relied on variations of the 567 engine. From the late 1930s through the 1960s, the 567 in its various iterations was the heart of EMD's locomotive line, and EMD dominated the market. But by the mid-1960s, railroads were demanding more power. The horsepower race was heating up. Trains were getting longer and heavier. Competition from General Electric was intensifying. EMD needed an engine that could produce significantly more power without being drastically larger or heavier. The answer was the 645 engine, introduced in 1965. The designation followed the same logic: 645 cubic inches of displacement per cylinder, achieved by increasing the bore of the cylinders compared to the 567. The 645 engine was transformative. It powered the locomotives that defined modern railroading in the 1960s and 1970s. The GP38 and GP40 used 645 engines. The SD40 and SD45 were 645 powered, and most significantly, the legendary SD40T2, which became the most successful 6-axle locomotive ever built in North America, relied on the 16-cylinder 645E3 engine, producing 3,000 horsepower. The 645 proved to be exceptionally reliable, mechanically robust, and easy to maintain. It established EMD's reputation for building engines that simply worked year after year with minimal drama. But by the late 1970s and early 1980s, the railroad industry was changing again, and the demands on locomotive engines were evolving. Railroads wanted even more horsepower to reduce the number of units needed per train. They wanted better fuel efficiency to combat rising energy costs following the oil crises of the 1970s. They wanted lower emissions as environmental regulations began tightening. They wanted engines that could run longer between overhauls, reducing maintenance costs and improving availability. And they wanted all of this without sacrificing the reliability that EMD engines were known for. The 645 engine was approaching its practical limits. You could only push the displacement and cylinder pressures so far before reliability suffered. Turbocharging could extract more power, but it also increased thermal and mechanical stresses. The SD45, with its turbocharged 20-cylinder 645 engine producing 3,600 horsepower, had proven powerful, but also demonstrated that pushing the 645 too hard led to maintenance challenges. Railroads liked power, but they loved reliability more. What was needed was an engine that could deliver substantially more horsepower than the standard 645, while maintaining or even improving reliability. EMD's engineers faced a fundamental question. Could they design a new engine that would be as successful as the 567 and 645 had been? Could they create something that would power locomotives for decades, become the standard by which other engines were judged, and establish EMD's dominance for another generation? The pressure was immense. General Electric was gaining market share with their 7FDL engine series, offering competitive power and increasingly competitive reliability. EMD couldn't afford a misstep. The development philosophy was characteristically EMD, evolution rather than revolution. They wouldn't abandon the two-stroke cycle that had served them so well. They wouldn't radically redesign the basic architecture. Instead, they would take the proven 645 design and systematically improve every aspect. More displacement per cylinder, yes, but achieved through careful engineering rather than simply making everything bigger. Better turbocharging for improved airflow, enhanced cooling systems for the higher heat loads, improved fuel injection for better combustion efficiency, stronger components where analysis showed they were needed, refinement of manufacturing processes to improve quality and reduce variation. The goal was ambitious. Create an engine family that could span from 2,000 horsepower for switchers and passenger locomotives up to 4,000 horsepower and beyond for heavy freight service. Make it scalable, available in V8, V12, and V16 configurations to suit different applications. Ensure it could be manufactured on existing production lines with minimal retooling. Design it to be maintainable using similar procedures and tools as the 645, so railroad shop forces wouldn't need extensive retraining. And above all, make it reliable enough that railroads would trust it with their most important trains from day one. This was the challenge EMD set for themselves in the early 1980s. The result of that effort would reshape the locomotive industry and power North American railroading for the next 4 decades and counting. The 567 had launched the diesel era, the 645 had perfected it, the 710 would define its modern age. EMD's engineers weren't trying to reinvent the diesel engine when they began development of the 710. They were trying to perfect it. The fundamental question was simple. How do you get more power from a diesel engine without compromising reliability? The answer, as it turned out, required rethinking dozens of details while preserving the core principles that had made EMD engines successful. The most straightforward way to increase power is to increase displacement, the volume of air and fuel that can be burned with each power stroke. EMD achieved this by lengthening the piston stroke while keeping the cylinder bore the same as the 645. The stroke increased from 10 inches to 11 inches, which increased the displacement per cylinder from 645 cubic inches to 710 cubic inches. That's where the name came from, following EMD's tradition of naming engines after their cylinder displacement. This might sound like a simple change, but it had cascading effects throughout the engine design. A longer stroke means the piston travels farther during each cycle, which increases the forces on connecting rods, crankshaft, and bearings. It changes the timing of valve events and affects how fuel burns in the cylinder. It alters the thermal loads on cylinder heads and liners. Every one of these effects had to be carefully analyzed and addressed. The connecting rods had to be stronger to handle the increased forces. EMD used improved steel alloys and refined the forging process to create components that were stronger without being significantly heavier. The crankshaft was redesigned with this same philosophy. Stronger where analysis showed higher stresses, but not simply made heavier throughout, which would have increased rotating mass and reduced engine responsiveness. The cylinder heads received particular attention. These components endure tremendous thermal stress, with combustion gases reaching temperatures over 3,000 degrees Fahrenheit, just inches from cooling water passages. The 710's higher power output meant even more heat to dissipate. EMD improved the cooling passages within the heads, optimizing water flow to remove heat more effectively. The exhaust valves, which operate in the hottest part of the combustion chamber, used improved materials that could withstand higher temperatures without failure. Turbocharging was critical to the 710's success. The turbocharger forces more air into the cylinders than they could draw in naturally, allowing more fuel to be burned and more power to be produced. But turbocharging introduces its own challenges. The compressed air gets hot, which reduces its density and limits how much can actually fit in the cylinder. The turbocharger itself must spin at extremely high speeds, often over 100,000 revolutions per minute, while handling exhaust gases at extreme temperatures. EMD's solution was a mechanically assisted turbocharger system. At low engine speeds, a mechanically driven Roots blower provided air to the cylinders, ensuring good low-speed torque and smooth power delivery. As engine speed increased, the turbocharger took over, driven by the energy in the exhaust gases. This combination gave the 710 excellent power characteristics across its entire operating range. There was no turbo lag, no dead spots in the power curve. From idle to full throttle, power delivery was smooth and predictable. The air-to-air intercooler was another important component. After being compressed by the turbocharger, air passed through the intercooler, where it was cooled before entering the cylinders. Cooler air is denser, containing more oxygen per unit volume, which allows more complete fuel combustion and higher power output. The intercooler also reduced thermal stress on engine components by keeping intake air temperatures in check. Fuel injection required careful development. The 710 used unit injectors, individual fuel injection pumps for each cylinder. These were mechanically operated by the engine's camshaft, using pushrods and rocker arms similar to those that operated the exhaust valves. Unit injectors provided extremely high injection pressures, which atomized the fuel into a fine mist that burned more completely. The timing of injection was critical. Inject too early, and you get harsh combustion and increased emissions. Too late, and you lose power and efficiency. EMD spent considerable development time optimizing injection timing for different load conditions. The camshaft profile, the shape of the lobes that operated the valves and fuel injectors, was completely redesigned for the 710. The cam profiles controlled when and how quickly valves opened and closed, which affected everything from power output to emissions to mechanical stress. EMD used computer analysis to optimize these profiles, something that wasn't possible when the 5on67 and 645 were designed. The result was better breathing, more complete combustion, and smoother operation. Cooling system capacity had to increase to handle the additional heat generated by higher power output. The 710 produced more heat not just because it made more power, but because it packed that power into the same basic envelope as the 6on45. The radiator sections were redesigned with more surface area and improved airflow characteristics. Cooling fans were more powerful, capable of moving larger volumes of air through the radiators. The entire cooling system was engineered as an integrated package rather than just sizing individual components larger. The electrical system needed updating as well. The alternator had to produce more electrical power to match the engine's increased output. EMD developed new alternator designs capable of handling 4,000 horsepower and beyond. The electrical control systems were updated with solid-state electronics that provided better load management and more precise control of traction motor current. These improvements weren't just about handling more power. They also improved reliability and reduced maintenance requirements. EMD designed the 710 to be a family of engines rather than a single model. The V16 configuration, with 16 cylinders, would be the workhorse for heavy freight locomotives. The V12 would serve medium-duty applications and some passenger locomotives. The V8 would power switchers and light passenger units. All would share the same basic architecture, the same cylinder design, the same major components. This parts commonality reduced manufacturing costs, simplified spare parts inventory, and allowed maintenance knowledge to transfer between models. The first 710 engines began testing in the early 1980s. EMD subjected them to brutal evaluation, sustained full power operation for thousands of hours, rapid load cycling to simulate switching service, operation in temperature extremes, analysis of wear patterns and failure modes. They tore down test engines repeatedly to measure component wear and verify that parts were lasting as long as predicted. When problems were discovered, they were addressed before production began. In 1984, EMD was ready to introduce the 710 to the railroad industry. The locomotive that would carry it was the SD-60, a six-axle freight unit designed to produce 3,800 horsepower from a 16-cylinder 710 G3 engine. This was 800 horsepower more than the SD-42, achieved in the same size locomotive, with promises of better fuel efficiency and comparable reliability. Railroads were skeptical. They had learned to trust the 645 engine, and any new design would have to prove itself in service. But EMD was confident. They had done the engineering work. They had tested thoroughly. The 710 was ready. What EMD couldn't know in 1984 was just how successful the 710 would become. It would power the locomotives that defined modern railroading. It would prove adaptable to changing emissions standards, new traction technologies, and evolving operational demands. It would become as fundamental to late 20th and early 21st century railroading as the 567 had been to the diesel revolution, and the 645 had been to the 1960s and 1970s. The 710 wasn't just a new engine. It was the engine that would carry EMD and the railroads into the modern era. Understanding what makes the 710 engine exceptional requires looking at its systems in detail. This isn't just an academic exercise. Every one of these systems was carefully engineered to contribute to the overall goals of power, reliability, efficiency, and maintainability. The 710 succeeded because EMD got all the details right. The prime mover itself is the foundation of everything. The 710 is a two-stroke diesel engine, which means each cylinder fires once per crankshaft revolution. This is fundamentally different from the four-stroke engines most people are familiar with in automotive applications. In a four-stroke engine, each cylinder fires once every 2 revolutions: intake, compression, power, exhaust. In a two-stroke engine, intake and exhaust occur simultaneously as the piston passes through bottom dead center, and each upward stroke is a power stroke. This gives two-stroke engines smoother power delivery and excellent low-speed torque, characteristics that are ideal for locomotive service. The VAE-16 configuration, the most common 710 variant, has 16 cylinders arranged in a 45-degree V formation. Each cylinder displaces 710 cubic inches, giving the engine a total displacement of 11,360 cubic inches, or about 186 liters. To put that in perspective, a typical automotive engine might displace 3 or 4 liters. The 710 is enormous by any standard, yet it's remarkably compact for the power it produces. At 900 revolutions per minute, the standard operating speed, a V16 710 produces between 3,800 and 4,300 horsepower, depending on the specific model and turbocharger configuration. That's enough power to pull a mile-long freight train up a mountain grade or accelerate a passenger train to up 100 miles per hour. Each cylinder is a complete power assembly that can be removed individually for service. This modularity is one of EMD's fundamental design principles, carried forward from the 567 and 645 engines. A power assembly consists of the cylinder liner, piston, connecting rod, and associated components. If one cylinder develops problems, perhaps a scored liner or worn piston rings, that power assembly can be pulled without disturbing the rest of the engine. A shop equipped with proper lifting equipment can remove and replace a power assembly in several hours. This means repairs that might require a complete engine replacement on other designs can be handled as relatively routine maintenance on the 710. The turbocharging system is sophisticated and critical to the engine's performance. The exhaust from all 16 cylinders flows to the turbocharger, spinning a turbine wheel at extraordinary speeds. That turbine drives a compressor wheel on the opposite end of the same shaft, and the compressor forces air into the engine's airbox. The airbox is a pressurized chamber that surrounds the cylinders, and from there, air flows through ports into the cylinders during the intake phase of operation. But the 710 doesn't rely on the turbocharger alone. It also has a mechanically driven Roots blower, a positive displacement air pump driven by gears from the engine's crankshaft. This blower functions as a scavenging pump, particularly important at low engine speeds when there isn't enough exhaust energy to drive the turbocharger effectively. The combination of mechanical blower and turbocharger gives the 710 excellent power characteristics from idle to full throttle. There's no waiting for the turbo to spool up, no lag in power delivery. The engine responds immediately to throttle changes, which is exactly what railroad service demands. The air entering the engine is hot after being compressed by the turbocharger, often 250 to 300 degrees Fahrenheit or more. This hot air is less dense than cool air, which limits how much can fit in the cylinders. The intercooler solves this problem. It's a large heat exchanger, similar to a radiator, through which the compressed air passes after leaving the turbocharger. Cooling water flows through passages in the intercooler, absorbing heat from the air. The cooled air, now denser and containing more oxygen, then flows to the engine's airbox. This cooling typically reduces air temperature by 100 to 150 degrees, which translates directly into more power and better fuel efficiency. Fuel injection in the 710 uses unit injectors, one per cylinder. These are mechanically operated by the engine's camshaft through a system of push rods and rocker arms. When the camshaft lobe rises, it pushes the rocker arm, which forces a plunger down into the injector body. This creates extremely high pressure, over 20,000 pounds per square inch, that forces fuel through tiny nozzle openings into the combustion chamber. The high pressure atomizes the fuel into a fine mist that mixes thoroughly with the compressed air and burns cleanly and completely. The timing of injection is crucial. Inject too early in the compression stroke and you get rough combustion, excessive peak pressures, and increased mechanical stress. Inject too late, and combustion isn't complete by the time the exhaust ports open, which wastes fuel and increases emissions. EMD optimized injection timing for a balance of power, efficiency, and durability. The camshaft profiles that control this timing were developed through extensive testing and computer modeling to achieve ideal combustion characteristics across the engine's operating range. The exhaust valves deserve special attention because they work in one of the harshest environments in the entire engine. Immediately after combustion, when the cylinder is filled with gases at 3,000 degrees Fahrenheit and immense pressure, the exhaust valve must open and allow those gases to escape. The valve itself gets incredibly hot, and it must do this thousands of times per minute without failure. The 710's exhaust valves use special heat-resistant alloys. They're hollow and filled with sodium, which melts at operating temperature and helps conduct heat away from the valve head to the cooler stem and guide. The valve seats, the surfaces that seal against the cylinder head, are carefully machined and use hard-facing materials to resist erosion from hot exhaust gases. The cooling system is engineered to remove enormous amounts of heat from the engine. Combustion of diesel fuel produces tremendous thermal energy, and only about 30 to 40% of that energy becomes useful mechanical power. The rest is heat that must be dissipated. Cooling water circulates through passages in the cylinder liners, cylinder heads, and intercooler, absorbing heat as it goes. Hot water flows to radiator sections at the rear of the locomotive, where it passes through thousands of small tubes. Air blown through the radiators by powerful electric fans removes heat from the water, and the cooled water returns to the engine to repeat the cycle. The radiator capacity on 710-powered locomotives is substantial. Multiple large radiator sections provide enough heat rejection capacity to keep the engine cool even at sustained full throttle in hot weather. The cooling fans are sized to move massive volumes of air, often over 100,000 cubic feet per minute. The entire cooling system is controlled by thermostats and electronic systems that adjust fan speed based on coolant temperature, ensuring the engine always operates within its optimal temperature range. Lubrication is critical to engine longevity. The crankshaft, connecting rods, piston pins, camshaft, and countless other components all rely on pressurized oil for lubrication. An engine-driven oil pump circulates oil through passages drilled in the crankshaft and cylinder block, delivering it to every bearing surface. The oil not only lubricates, but also helps cool components, particularly the underside of the pistons, which are exposed to combustion heat. The oil then drains back to a sump, where it's cooled, filtered, and recirculated. EMD specifies oil change intervals and filter replacement schedules designed to keep oil clean and effective, preventing wear and extending component life. The electrical generation system converts the mechanical power from the engine into electrical power for the traction motors. In most 710-powered locomotives, an AR11 or AR20 alternator is mounted directly to the engine and driven through gears. This alternator produces three-phase AC electricity. In locomotives with DC traction motors, this AC is rectified to DC by banks of silicon diodes before being fed to the motors. In AC traction locomotives, the AC from the alternator goes to inverters, sophisticated electronic systems that convert it to variable frequency AC, precisely controlled to match traction motor requirements. The control system integrates all these systems into a coordinated whole. When the engineer moves the throttle, the control system adjusts fuel injection rate, turbocharger boost pressure, cooling fan speed, alternator field strength, and traction motor current. Everything is orchestrated to provide smooth, predictable power delivery while protecting the engine from damage. Over-temperature conditions reduce power automatically. Low oil pressure triggers warnings and eventually shutdowns. The control system constantly monitors dozens of parameters and adjusts operation to keep everything within safe limits. Maintenance accessibility was a key design goal. Major components can be reached without extensive disassembly. The cylinder head can be removed for valve service without pulling the entire power assembly. Fuel injectors can be changed relatively quickly. Turbocharger maintenance is facilitated by good access and quick disconnect fittings. EMD learned from decades of field experience exactly what maintenance tasks were most common and ensured those tasks could be performed efficiently. The result of all this engineering is an engine that simply works. It produces prodigious power from a compact package. It does so reliably, year after year. It can be maintained by competent diesel mechanics without exotic tools or specialized training. It adapts to different applications through variations in configuration and tuning, and it's proven durable enough that engines built in the 1980s are still in service today, many having been through multiple rebuilds, still producing power and earning revenue for their operators. This is what makes the 710 exceptional, not any single revolutionary feature, but the comprehensive integration of well-engineered systems into a reliable, powerful, maintainable whole. EMD took everything they had learned from the 5N67 and 6N45 engines, applied modern engineering analysis and manufacturing techniques, and created an engine that would define locomotive power for a generation. The details matter, and EMD got them right. The 710 engine didn't just power locomotives. It powered an entire generation of railroading. From the mid-1980s through the present day, 710-powered locomotives have been the backbone of North American freight and passenger service. Understanding the 710's impact requires looking at the locomotives it powered and the roles they played. Freight locomotives, the heavy haulers. The SD60 was the first, introduced in 1984 as EMD's new standard freight locomotive. With its 16-cylinder 710G3 engine producing 3,800 horsepower, it offered substantial power increase over the SD42 it was meant to supplement and eventually replace. The SD60 looked different from earlier EMD locomotives, with a wider cab and more angular design reflecting modern styling. But underneath, it was all business: 3,800 horsepower, 6-axle traction, and the reliability railroads had come to expect from EMD. Initial buyers included Conrail, Burlington Northern, Soo Line, and Union Pacific. These railroads put the SD60s to work on demanding assignments, coal trains, heavy manifest freights, intermodal consists. The locomotives performed well, and the 710 engine proved itself in service. It delivered the promised power. It was reliable. Fuel consumption was competitive. The SD60 validated EMD's confidence in their new engine, but the SD60 was just the beginning. In 1993, EMD introduced the SD70, which would become one of the defining locomotives of modern railroading. The SD70 family included multiple variants, each addressing specific operational needs. The SD70M used a 16-cylinder 710G3B engine producing 4,000 horsepower, another significant increase over the SD60. It featured an isolated cab mounted on rubber supports to reduce noise and vibration for crew comfort. The electrical system used modern microprocessor controls for precise load management. Burlington Northern Santa Fe ordered hundreds of SD70Ms, making them a common sight across the western United States. Union Pacific, Kansas City Southern, and other railroads also operated SD70Ns extensively. The SD70 MAC represented a technological revolution. The designation MAC stood for Modular AC, referring to AC traction motors instead of the traditional DC motors used in earlier locomotives. AC traction provided superior adhesion, particularly in heavy-haul coal service. The same 710G3B engine producing 4,000 horsepower, but with AC traction, an SD70M AC could pull heavier trains with less wheel slip, particularly on steep grades and adverse weather. Burlington Northern Santa Fe was the primary operator of SD70 Max, eventually owning over 1,000 units. They used them primarily in coal service, hauling massive unit trains from the Powder River Basin in Wyoming to power plants across the country. The SD70 Max combination of 710 power and AC traction revolutionized heavy-haul railroading. Trains that once required multiple locomotives could be handled with fewer units. Wheel slip, a constant problem with DC locomotives in heavy service, was dramatically reduced. The SD70 Mac proved so successful that AC traction became the standard for heavy freight locomotives industry-wide. The SD70 ACE, introduced in the early 2000s, was EMD's response to increasingly strict emissions regulations. The AC designation indicated it met EPA Tier 2 standards for diesel emissions. The engine was a 16-710G3C T2, a variant of the basic 710 design, with modifications to reduce emissions while maintaining 4,000 horsepower. These modifications included improved fuel injection, enhanced air management, and sophisticated electronic controls that optimize combustion. Every major North American Class I railroad operated SD70ACs. Union Pacific ordered hundreds. Norfolk Southern bought them in quantity. Canadian National and Canadian Pacific both ran SD70AC fleets. Kansas City Southern used them as standard power. The SD70AC became the modern American freight locomotive, as ubiquitous in the 2000s and 2010s as the SD482 had been in the 1970s and 1980s. And at the heart of everyone was a 710 engine, still using the basic design introduced in 1984, now refined to meet modern standards. Export models extended the 710's reach globally. EMD built 710-powered locomotives for Brazil, where they hauled iron ore and agricultural products. Saudi Arabia purchased large fleets for moving petroleum products. Australia ordered heavy-haul locomotives for mining operations, with some units configured with 3 trucks for massive tonnage capability. The 710's reliability translated well to international service, proving it wasn't just suited to North American conditions, but could handle whatever was asked of it anywhere in the world. Passenger locomotives, speed and reliability. The 710 found equally important roles in passenger service, where reliability was absolutely critical. A freight locomotive breakdown delays a train and costs money. A passenger locomotive failure strands hundreds of people and makes headlines. Passenger operators needed power they could trust completely. The F59PH and F59PHI became the faces of North American passenger railroading in the 1990s and 2000s. These locomotives used a 12-cylinder 710G3B engine producing 3,000 horsepower. The streamlined carbide design, with its distinctive angled nose, became immediately recognizable. Amtrak operated them on corridor services, commuter railroads across North America, Metrolink in Southern California, Caltrain in the San Francisco Bay Area, GO Transit in Toronto, West Coast Express in Vancouver, and dozens of others relied on F59 PHIs for daily service, moving hundreds of thousands of commuters. The F59 PHI proved ideal for passenger work. The 710 engine provided ample power for accelerating heavy passenger trains to track speed quickly. The head-end power system, which used engine power to generate electricity for passenger car heating, air conditioning, and lighting, worked reliably. The locomotives were comfortable to operate, with good visibility and modern cab amenities, and crucially, they were dependable. Day after day, year after year, F59 PHIs started reliably and moved their trains on schedule. For commuter railroads where delays cascade into operational chaos, this reliability was invaluable. The DE30AC and DM30AC were specialized locomotives built for the Long Island Railroad. These used 12-cylinder 710 engines and were designed to operate both from diesel power and third-rail electric power in the electrified portions of Lear's system. The complexity of dual-mode operation required sophisticated engineering, but the 710 engine provided the reliable foundation that made these challenging locomotives successful. VIA Rail Canada operated F40PH3s and 42DCs with 710 power on long-distance services. These locomotives pulled passenger trains across thousands of miles of Canadian territory, from the maritime provinces to the Pacific coast. The 710 engines handled everything from humid summer heat in Ontario to brutal winter cold in the prairies to mountain grades in British Columbia. The ability to start reliably in -40-degree weather and pull heavy trains through Rogers Pass was a testament to the engine's robustness. Marine and industrial applications. The 710's success extended beyond railroads. The marine industry adopted 710 engines for tugboats, offshore supply vessels, and other applications where reliable, compact power was essential. A tugboat pushing barges on the Mississippi River or a supply vessel servicing offshore oil platforms needed power plants that wouldn't fail. The 710's reputation for reliability made it attractive for these demanding services. Industrial power generation was another market. Standby generators at hospitals, data centers, and critical facilities use 710 engines to provide backup power during electrical outages. The same characteristics that made the 710 successful in locomotives, reliable starting, steady power output, ability to handle sustained full load, made it ideal for emergency power generation. Some industrial facilities use 710 engines in stationary installations for continuous power generation, particularly in remote locations where connection to electrical grids was impractical. Mining operations, offshore platforms, and large construction projects all found uses for 710-based generating sets. The breadth of applications demonstrated that EMD had created more than just a good locomotive engine. They had created a versatile power plant suitable for any application requiring reliable diesel power in the 1,500 to 4,300 horsepower range. The 710 worked on rails, on water, and in stationary installations. It worked in tropical heat and Arctic cold. It worked at sea level and at high altitude. This universal capability validated the fundamental soundness of the design, the common thread. What united all these applications, freight, passenger, marine, industrial, was the need for reliable power. None of these operators could tolerate frequent failures. A locomotive that spent more time in the shop than on the road was worthless, regardless of how much power it made when it was running. The 710 delivered on reliability consistently across all applications, in all conditions. That's why it became the standard. That's why railroads kept ordering 710-powered locomotives, even as competing designs offered similar specifications. The 710 had proven itself, and proven reliability is worth more than paper specifications. From the SD60 in 1984 to locomotives still being built today, the 710 has powered thousands of locomotives and millions of miles of service. It's hauled coal from Wyoming, moved containers from California, carried commuters in Toronto, pulled ore trains in Australia, and powered countless other operations. It's been the background power for North American commerce and transportation for 4 decades. And it's not done yet. Even as EPA emissions requirements tightened through the 2000s and 2010s, the 710 didn't fade away. It evolved. EMD and locomotive rebuild companies developed programs to update older 710 engines to meet modern standards while preserving the reliability that made them valuable in the first place. This adaptability has been key to the 710's longevity. The progression of EPA tier standards drove much of this evolution. Tier 0, which applied to locomotives built before 2000, had relatively lenient emissions limits. Tier 1, effective from 2000 to 2004, tightened standards moderately. Tier 2, from 2005 to 2011, required significant reductions in nitrogen oxides and particulate emissions. Tier 3 and Tier 4, the current standards, demand even cleaner operation through sophisticated exhaust treatment and engine management. EMD developed tier-compliant versions of the 710 engine for each standard. The 710G3CT2, used in SD70UAC locomotives, met Tier 2 standards through improved fuel injection timing, optimized turbocharger management, and refined combustion chamber design. These changes reduced emissions significantly while maintaining 4,000 horsepower output. The engine was still fundamentally a 710, same displacement, same basic architecture, but refined to burn fuel more cleanly. The 710 ECO Repower program took this further. This program involved taking older locomotives with non-compliant 710 engines and completely rebuilding them with updated tier-compliant engines and modern control systems. A locomotive built in the 1990s with a Tier 0 engine could be transformed into an essentially new locomotive meeting modern emission standards. The economics were compelling. Comprehensive rebuild and repower cost perhaps 40 to 50% of new locomotive price while delivering similar performance and emissions compliance. Progress Rail, owned by Caterpillar and a major player in locomotive rebuilding, offered extensive 710 rebuild programs. They would take a complete locomotive, strip it down, rebuild the engine with updated components, modernize the electrical systems, refurbish the trucks and running gear, and produce what was essentially a new locomotive at substantial cost savings compared to new construction. Electromotive diesel, as EMD became known after various ownership changes, continued developing the 710 for modern applications. The two-stroke diesel cycle, which had served EMD so well for over 80 years, beginning with the 567, faced fundamental challenges meeting Tier 4 emission standards. The challenge of achieving Tier 4 compliance while maintaining reliability and power density led EMD to eventually develop a new four-stroke engine family. However, the 710 remained in production for certain applications and continued to be supported for the enormous installed base of existing locomotives. Railroads with large fleets of 710-powered locomotives invested heavily in maintaining and upgrading them rather than replacing them. The economic logic was straightforward. A well-maintained 710 engine could run for 15 to 20 years or more between major overhauls. After an overhaul, which involved complete disassembly, inspection, replacement of worn parts, and reassembly to original specifications, the engine was essentially new again and ready for another service cycle. A locomotive with a properly maintained 710 could remain in service for 30, 40, even 50 years through multiple rebuild cycles. Union Pacific, one of the largest railroads in North America, maintained a massive fleet of SD70Ms and SD70ACs with 710 engines. Rather than retire these locomotives, UP invested in systematic maintenance and selective rebuilding to keep them operating efficiently. The 710's reliability in heavy coal and manifest freight service made this investment worthwhile. BNSF Railway operated over 1,000 SD70 Max, all with 710 engines, primarily in coal service. These locomotives worked some of the most demanding service in North America: heavy unit trains, steep grades, high annual mileage. BNSF developed comprehensive maintenance programs specifically for their SD70 ASAC fleet, including scheduled engine overhauls, truck rebuilds, and electrical system updates. The 710 engines, when properly maintained, proved capable of handling this service for decades. Canadian National and Canadian Pacific both operated large 710-powered fleets and similarly invested in keeping them running. The economics of railroad operations meant that locomotives were assets to be maintained and used as long as they remained productive. The 710's design, with its modular construction, available parts, and well-understood maintenance requirements, made long-term operation practical and economical. Tier 4 emission standards, implemented in 2015, presented the biggest challenge. Meeting these stringent limits required exhaust after-treatment systems, selective catalytic reduction to reduce nitrogen oxides, diesel particulate filters to trap soot that added complexity and maintenance requirements. EMD chose to develop a new engine family rather than continue evolving the 710 for Tier 4 compliance. However, this didn't make existing 710 engines obsolete. Locomotives built before 2015 weren't required to meet Tier 4 standards, and the installed base of 710-powered locomotives remained enormous. The flexibility of the 710 design allowed it to adapt to changing requirements in ways that extended its relevance. Need more power? Adjust turbocharger boost and fuel injection, need better fuel economy, optimize injection timing, and improve combustion efficiency. Need lower emissions, refine air management and combustion parameters. Within limits, the 710 could be tuned to emphasize different performance characteristics, making it suitable for a wide range of applications even as priorities shifted. Locomotive leasing companies, JTX, CIT Group, and others maintained large fleets of 710-powered locomotives, available for short-term and long-term lease to railroads. When a railroad needed extra power for seasonal traffic surges or to cover units in the shop, they could lease 710-powered SD70s or SD60s and know exactly what they were getting. This fungibility added value to 710-powered locomotives in the secondary market. The aftermarket for 710 parts and services remained robust. Remanufacturers offered rebuilt turbochargers, alternators, and complete power assemblies. Suppliers stocked filters, injectors, gaskets, and wear items. The installed base was large enough that supporting it remained commercially viable, which in turn made long-term 710 operation practical for locomotive owners. Export markets continued ordering 710-powered locomotives long after North American emission standards would have prohibited them for domestic service. Countries with less stringent environmental regulations still valued the 710's power and reliability. EMD and other manufacturers built locomotives with 710 engines specifically for export, ensuring the engine remained in production. The longevity of the 710 design, approaching 40 years in production with thousands of units still in active service, validated EMD's engineering approach. They had built an engine that could evolve with changing requirements, that could be maintained economically, that continued providing value decades after introduction. This kind of long-term success is rare in any industry and speaks to the fundamental quality of the original design. The EMD 710 engine wasn't a revolution. It was evolution done perfectly, built on the foundation of EMD's two-stroke diesel heritage, refined with modern engineering analysis and manufacturing techniques, and proven through millions of miles of service. The 710 became one of the most successful diesel engines ever designed for railroad service. What made it successful wasn't any single breakthrough innovation. It was the comprehensive excellence of the entire design. The power density, 4,000 horsepower, from a package compact enough to fit in a standard locomotive frame. The reliability, engines running for decades with proper maintenance. The maintainability, modular construction, allowing component replacement without complete teardowns. The flexibility, adaptable to freight, passenger, marine, and industrial applications. The longevity, engines built in the 1980s still working today. All of these characteristics, integrated into a single design, created an engine that simply worked year after year in whatever service it was assigned. The locomotives powered by 710 engines transformed North American railroading. The SD60 provided power increases that improved productivity. The SD70 enabled the AC traction revolution that changed the heavy-haul freight. The F59 PHI became the face of passenger railroading for a generation. The SD70AC proved that power and emissions compliance could coexist. Together, these locomotives and dozens of other models carried the railroad industry from the 1980s into the 21st century. The people who worked with 710 engines developed deep respect for them. Engineers appreciated the smooth power delivery and predictable performance. Maintenance forces valued the straightforward service procedures and available parts. Operations personnel trusted them to move trains reliably, on schedule, without the surprises that plagued less mature designs. This trust, built over decades of consistent performance, made the 710 more than just an engine. It made it the standard by which other designs were judged. The sound of a 710 engine, the steady idle, the rising note as throttle advances, the distinctive turbocharger whistle under load, became part of the soundtrack of modern railroading. Anyone who stood trackside as an SD70 accelerates with a heavy freight. Anyone who's waited at a crossing as an F59 PHI pulls a commuter train. Anyone who's watched coal trains climb mountain grades behind SD70 Max, they've heard the 710. That sound has been the background of North American commerce and transportation for 40 years. Visually, 710-powered locomotives defined what modern freight and passenger power looks like. The SD70 series, in all its variants, became as iconic as the SD42 had been a generation earlier. The F59 PHI's streamlined nose became synonymous with passenger service. When people picture a modern American locomotive, they're often picturing a 710-powered machine, even if they don't realize it. The technical legacy of the 710 extends beyond the engine itself. The development methodologies EMD used, computer-aided design, finite element analysis, extensive prototype testing, became industry standard. The emissions reduction techniques pioneered on 710 variants informed subsequent engine designs throughout the diesel industry. The AC traction systems integrated with 710 power revolutionized locomotive performance industry-wide. The 710 was part of a broader evolution in locomotive technology, and it proved that traditional design philosophies could successfully incorporate modern innovations. The economic impact is harder to quantify, but no less significant. The 710 powered the locomotives that moved trillions of dollars worth of freight. It enabled coal-fired power plants to receive fuel efficiently. It moved containers from ports to distribution centers. It carried millions of commuters to work. The economic activity enabled by reliable locomotive power is enormous, and the 710 was a crucial part of that infrastructure for 4 decades. What's perhaps most remarkable is that the 710 story isn't over. Engines built in the 1980s and 1990s are still working, still being maintained, still earning revenue for their operators. New applications continue being found for rebuilt 710-powered locomotives. The installed base is so large that the 710 will remain relevant for years to come. Some locomotives being operated today by young engineers weren't even born when these engines were built. Yet the engines continue doing their job as if age is irrelevant. The 710 proved that the two-stroke diesel cycle EMD pioneered in the 1930s could remain competitive into the 21st century. While emissions regulations eventually drove the industry toward other solutions, the 710 showed that traditional designs, continuously refined, could adapt and evolve far longer than many had predicted. This is a lesson that extends beyond locomotives. Sometimes the best answer isn't the newest technology, but the proven technology, refined. In an industry that demands reliability above all else, where locomotive failures mean delayed trains, dissatisfied customers, and lost revenue, the 710 delivered consistency. It showed up every day and did its job. It pulled trains, generated power, moved freight and passengers without drama or excessive maintenance. That kind of reliability, sustained over decades, is the highest compliment any engine can receive. Today, as railroads operate increasingly sophisticated locomotives with computer controls, advanced emission systems, and cutting-edge technology, thousands of 710 engines continue working. They're in SD70ACs pulling intermodal trains across the plains. They're in F59 PHIs moving commuters in morning rush hours. They're in rebuilt SD60s working secondary service on short lines. They're still out there, still proving that good engineering doesn't age, still demonstrating that power, reliability, and longevity can coexist in a single design. The EMD 710 engine redefined modern diesel power, not through revolutionary technology, but through evolutionary excellence. It took proven principles, refined them with modern engineering, and created a power plant that served the railroad industry faithfully for 4 decades and counting. It powered freight, passengers, cities, ports, and nations. And even today, almost 40 years after the first 710 rolled off the assembly line, it's still going, still working. Still proving that the best machines are the ones that simply won't quit. EMD 710, 1984 to today, the engine that redefined modern diesel power.